So welcome back. So the first speaker of this afternoon is Gavril Farkas from Humboldt-University in Berlin. So he will talk about birational geometry of MG via tropical geometry and non-abelian Brill-Noether theory. Please.
Yeah, so thank you very much for the invitation to be in Taipei again. It's my first time in 20 years. So I will talk about a problem that is classical in every sense of the word, and the question is concerning the birational nature of the moduli space of curves, right? So what is the Kodaira dimension of MG? And Jumuk said today that about rational tangents, he has considered this problem a long time. I also considered this problem for a long time. And that problem indeed has been considered by a lot of people. And there is results that MG is a unirational variety for low genus. And this for G less than 10, this is due to Severi. This is 1915, yeah. This was long before the space was shown to exist, but he was not bothered by this. Then same for genus 11, 12, 13, 14. So this is more modern mathematics, and these are due to Cernesi, Changran, and to Vera. So this is 80s, 90s, 2000, Vera is 2015. So there are all sorts of proofs and approaches. They are different. Some are even correct. And in any case, it's a very nice result. And that's a different story. Rational, okay, since Claire asked, I think G up to 6 is rational. I think not beyond that is not known. I'm pretty sure, yeah. So that's a different story. Yes, and this was then, I will add here also the name of Schreier. So these are results in the sense that, okay, if you have a unirational construction, then you can write down the curve of genus G in very concrete terms. And Schreier has implemented this in computer algebra and says you take, there are routines that produces the general curve of genus up to 14 over a finite field, for instance, right? So it's a very good state of affairs. And then M15 is rationally connected. And this is due to Bruno and Vera. And I will sort of revisit this. It's a very lovely construction. Okay, so this is what is known on this side of the story. What do you think? So, no. And on the other side, you know that MG is a general type. And this is a different story, so this is kind of negative result. And this was now done to genus 24 by, this is the 80s, one of the famous theorems in the 80s, and this is Harris, Mumford, Eisenbud. And 22 and 23 was achieved after a very long struggle this is due to myself, to Jensen and Payne. A very non-trivial tropical component. So this is the situation, yeah, of this classical problem. This is what's so, okay, you see there are some cases left. And okay, so I would like to say what I'm going to do today. So this is a theorem with Vera. That says that M16 is uniruled. So This is, despite the fact that there is a paper in Invenciones which asserts this result, that proof is not okay. But ours is okay. Checkmate final. So, of Zivran. Okay, so I will discuss, I will try to, so this is the last genus for which this is currently, you have a structure theorem is of some sorts for the general curve of genus G. Okay, so I will say something that probably most people know here. So this problem, of course, can be attacked, translated into a problem about effective divisors on the moduli space of curves. So I'll do a very quick recap on the Harris-Mumford-Eisenbach approach. And I will retain from it what I need for this, for what I want to say. Well, you know, MG has a compactification, and this compactification is ideal or God-given in every possible sense by stable curves. There is no need to improve on this. And there are boundary divisors, right? And the boundary divisors look like, you know, generic point of delta 0 is an irreducible curve with one node, and the generic point of delta I is a union of two curves of genera I and G minus I meeting transversely in a point. So these are, okay, so we have these divisors, and Harris and Mumford actually computed the class of the canonical on the coarse moduli space, and this is 13 times lambda is the Hodge class, minus 2 times delta 0, minus 3 times delta 1, minus 2 times delta 2, and so on. And then, okay, so up to a story about the singularities of the moduli space being almost canonical. They are not quite canonical, but they are not far from it. To show that MG bar is general type, it suffices to construct an effective divisor divisor D on MG bar, right? So a priori sections, you have to construct sections of this bundle. So this, if you think that these are sections coming from the moduli of abelian varieties, these should be kind of Siegel modular forms that don't vanish on MG bar, but this is a very difficult task, put it like this, and it was Mumford insight to geometrize this problem and say, all right, we are going to construct geometric divisors on moduli space of curves, an effective divisor D, and this D you can write as A lambda minus the sum of the BI delta I. So everything you can write like this because these are the generators of the Picard group, such that the slope, this invariant of the divisor, which is A divided by the minimum of the BI's, so this is the slope, this should be less than the slope of the canonical. This is 13 halves. Assume you can do this. Then, of course, you can say that K, the canonical, is a positive multiple of the Hodge class plus, no, this is not the same, it's a constant, plus some boundary, no, plus the effective divisor that we have constructed, plus some positive boundary. Yeah, so you can write it like this, where the constants alpha and beta are actually positive. And the mean, yeah, from 0 to 0 to G over 2. I take all the, yeah. Typically it's B0 here, yeah. But you have this. And then, okay, assume that you can do this, then out of this you can derive this implication. And now you know that lambda is almost an ample class. It's ample plus nef actually. It's nef and big on MG bar. So it has the maximal number of sections, and then this is ample plus effective, so this is a big class. And this is the same thing as saying that MG bar is of general type. So usually you have this reduction that you can, it's enough to construct a D with this property. So S of D, which has to have slope less than 13/2. So this is well understood. And then there is, okay, also conversely about uniruledness, if, on the other hand, you can show, so here you have to construct only 1D, yeah? And this is, you know, looking at these results for genus up to 14 or even 15, you will never find such a D. Such a D does not exist, yeah? But for higher genus it does exist. But so if you, on the other hand, S of D is always bigger than 13/2 for every D effective divisor, then you can deduce from this that the canonical of mg bar is not pseudo-effective. And using a famous theorem of Buxom, Campana, Peternel, Paun, I believe. So Buxom, Campana, Peternel, Paun. From this you deduce that it's uniruled. So you just have to inspect that this also works. I mean, these people prove this for smooth varieties, but MG has mild enough singularities that proof goes through. Yeah. So if you have to prove this, then you get uniruledness. And I'm going to use this criterion, in fact, for the case of M16. And so one disadvantage of this approach of Buxom and company is that it does not produce an explicit rational curve passing through the general point, but it does reduce the problem to. Yeah, I was almost sure that I was wrong about it, yeah. That I am missing a key character. But the others, Buxom, de Mailly, Peternel, Paun, okay. Right.
Why do you say it is an advantage?
It's a what?
Advantage.
It's not an advantage, it's a disadvantage. But sometimes that's all you can do. And this will be an instance of this, yeah. All right, okay. So anyway, I've summarized this discussion. So if you can prove that if you find a divisor of slope less than 6.5, then it's a general type. If you can prove that every divisor has slope bigger than 6.5, then it's uniruled. And if you are on the cusp, then it can go either way. Okay? So this is the situation. So now, of course, curves of genus 16 are complicated. Yeah. So you have to discover something that is about their structure. And so I still don't know how to write down the general curve of genus 16, even at the end of this paper, this result. I will sort of use this criteria to explain the proof of this result with Vera, but yeah, I will do it in 2 installments. At first, I would like to recall a couple of things about this result in genus 15. Yeah. Yeah, you need all the coefficients. No, so there is another principle that indeed in most cases delta 0 is the one that is the smallest coefficient. But a priori you need all, because otherwise you cannot write it something like this. You need really all the coefficients. Yeah. Okay, other questions? So let me then recall the parametrization, the Bruno-Vera parametrization of M15. So this is really wonderful in the sense it's very simple. And it says you start with a curve of genus 15. So see a general curve of genus 15. So you have to know a couple of things about it. It has gonality 9, and it has a one-dimensional family of G19s. So I'm using this, so W19, so this is the variety of pencils. It has no G18s, yeah? So it is general. This is one-dimensional, and by Riemann-Roch theorem, this is isomorphic to the W619. Yeah, so this is the, so yeah, so this is and both are, these are one-dimensional spaces. This comes from Brill-Noether theory. So if I start with, I have some cover of degree 9 of the curve. Well, this is only degree not 9, but never mind. So I have this. I take such a pencil A, and then I associate to it is the residual, which will be by Riemann-Roch. You can calculate. It will embed the curve in P6 with degree 19, right? So 9 plus 19, 28, 2g minus 2. Okay, so then you start to, okay, you look what surfaces contain this curve, and you make the following fundamental observation. You look at the multiplication map on quadrics of this, for this curve. And this is the multiplication map. So let's look at the dimensions. So this is, we are in P6, so this is 8 choose 2, which is 28. And this, so the curve satisfies the Petri theorem. So in particular, H1 of L squared is 0. So then you can compute this by Riemann-Roch. And by Riemann-Roch, this is 2 times 19 plus 1 minus 15, which is 24. And you can show that this map is of maximal rank. So this actually lies on 4 quadrics. So there exists 4 quadrics on which this curve lies. So let me write it like this. If I look at the base locus of the kernel of mu L, this will be the intersection of 4 quadrics in P6. So in particular, this should be a surface. Well, you have to prove, of course, all these things. This is a surface. And, surprise, surprise, this surface is a canonical surface. You have to prove it, but in general, it's smooth. So S in P6 is a canonical surface. It's a complete intersection of 4 quadrics in P6. Yeah? So this is why are we so happy to see a canonical surface? We are happy because of the following exact sequence. So C, any C can be put on a canonical surface in P6. And the point is now that this curve will move on this canonical surface. So I write down this exact sequence, yeah? And I would like to move the curve on the surface, so by a junction formula, what is this? This is omega C minus L, minus O of 1, yeah? Yeah, that's right, yeah. So, yes. So, and this is the pencil. So this is the pencil, right? So you see that, okay, so you get that the dimension of OS of C is in fact even 2. So you actually move the curve with 2 degrees of freedom. So this shows already that it's uni-ruled, right? The M15 is uni-ruled, and with a little bit of more work, you can show rational connectedness. So through a general point of M15 passes even a rational surface. There passes a rational surface. So this is, very, very good. I mean, this is very simple argument. It's hard for me to imagine how you can beat this. Yeah. There is a Noether-Lefschetz condition, and I have never done the calculation like this, but I would bet yes, it has to be. You impose the condition and yeah. Okay, so this is, so why am I doing this? This is for genus 15. I want to go to genus 1 higher. But the point is that there is some freedom here. And now I can lift this freedom. So, all right, so this was done by Bruno and Vera. And well, then there came this news that there is this problem with M16. And then I said, oh, no problem, I can fix this in no time at all. And here was the first approach. because I knew this parametrization of Brill-Noether. So of course the point is that I would like to lift this to the boundary divisor delta 0 in M16. So the boundary divisor delta 0 in M16, so I have a map from M15 to, so this is the two-pointed curves of genus 15 to delta 0 in M16, yeah? So this is the map that takes a curve like this with 2 points and identifies them, yeah? So this is a 2-to-1 map, and this is a map like this, a 2-to-1 cover. Most certainly. Thank you. Right? Okay. So then, if I now fix 2 points, there will be x and y are fixed. There will be, I have a one-dimensional family of such pencils, right? I haven't used yet the fact that there is one-dimensional family. Now, if I fix 2 points here, x and y, there will be finitely many such pencils which contain x and y in the same fiber. This is a one-dimensional condition, right? So given x, y on C, there's a finite number, non-zero finite number of A's, such a degree 9 covers, which contain x and y in the same fiber. Yes? So then I can do the same trick with this surface. I pick one of the A's that determines my L, and I carry the same construction through. And then I look now, I look at this exact sequence, and in fact there will be, I'm looking at those, I want to fix the points x and y. And for such an L, right? So for such an L, okay, so this is, for such an L, which is omega c minus a, the residual, we will observe now that in fact, if I look at the dimension of, so I can fix the 2 points. What is the dimension? So we just have to look at that sequence there, yeah? If you tensor everything with the ideal of the 2 points, I will get here a minus x minus y. And I get 2 sections. So projectively 1 section. So the dimension of this is 1. So there is in fact a curve that passes in M15-2 that passes through this point, through this 2-pointed curve, right? So that shows that there exists gamma 1, say, gamma 1, a curve in M15-2. No, it's fine. What? The dimension is 1. A projective 1, yeah. Yeah, so I had here 1 plus 2, 1 coming from here and 2 coming from here. Now I put the condition, x and y impose only 1 condition, so I will get still 1 here, but here I will get 1. So 1 plus 1 is 2, projective dimension 1. So there is I use it, so I look now this pencil, right? So the pencil, here's my surface, and here is my curve, yeah? And now I look at a pencil of curves passing through these 2 points. So they look like this. They are curves of genus 15 with 2 points. X and Y are fixed points. So this is actually a pencil in M15-2, and it's a covering curve in M15-2. So this argument shows that not only M15 is uni-ruled, but M15-2 is uni-ruled. Rational curve passing through this point. Yeah? So it's you lift, there was a little freedom there with the rational surface. And there was also a little freedom in choosing this pencil. So now we use everything. And we have shown that, in fact, the M15-2 is uni-ruled. It's not what we wanted yet, of course, but it's a step in the right direction. So we have produced at least a uni-ruled divisor in M16. So, any questions? So, okay. So now we would like to apply Buxom de Mailly paternal pool. Yes? So it's very simple well, it's not difficult to construct the so you understand so I have this curve in this pencil in M15 too, and well, what I get in M16 is I identify the points, the fixed points, right? And I got a curve in delta 0, which is in M16. So now I will compute so yeah, I hesitated, should I do calculations here publicly? And I will do calculations publicly. There is now nothing to stop me. Because otherwise it's silly, right? So let's do so I have this, so you understand, I fix the surface, and I move now the curve in this linear system. So now let's compute the intersection numbers with the classes. So this is, so basically I call this maybe gamma 1 prime. Yes, and then I call gamma 1 is this. So this is in M16. So this is gamma 1. So what are the intersection numbers? So this is not difficult. You just have to be a little bit lucky so that the result goes your way. So the intersection with lambda, so you are on a surface, on a canonical surface, and you have to remember what lambda means. But once you are so far, then you know that this is chi of OS plus G minus 1. This is for any pencil. And so this surface, this pencil has 9 base points, right? The 9 base points are the points in the fiber, the 9 points in the fiber over X and Y. So what is chi? Chi is, this is H0 minus H1 plus H2. So H0 is 1, H1 is 0, and H2, so we are talking about a canonical surface in P6. So H2 is equal to A0 of omega, and this is 7. So it's and G is 15. Yeah, it's because of genus 15. So it's 8 plus 14, 22. And then you have to compute the number of singular fibers in this pencil. Now, of course, away from the fact that everything there is this point here of so you have to compute the number of singular fibers in the pencil in M15. So there is a typical, this is basically this, it's a topological formula for computing the number of singular fibers in a pencil. It's no big deal. And it's the answer is C2 of the blown up surface. So S tilde is the blow up of S in these 9 points, plus 4 times G minus 1. So this you can believe me, these are general things. So this would be the answer for if I did a calculation in genus 15, but I do the calculation in genus 16 where I identify these 2 points. So then I have to subtract from this the self-intersection of the 2 psi classes. These are the normal bundles of the boundary divisor in M16 where I identify. So this is this formula. And it's immediate that these are actually, they are both, it's plus psi x squared plus, no, it's like this, yeah. So it's minus 2. Okay, so I have to do this calculation, and to do this calculation, yeah, the 9 point comes, I take a pencil on this curve passing through X and Y, and C squared on this surface is 9. The 9 points are the 9 points, yeah, there are more points here, 9. Yeah. In the W19, and I fix the point X and Y, so there will be X, Y, and 7 other points. Right, so let's do this. So we have also Noether formula. So I apologize, I am subjecting you to this. It's actually equal to Ks squared plus C2 of S, tilde. So I already established that chi is 8. So this is 96. And this is, what is Ks squared? So it's a 2 to 2 complete intersection. So this has degree 16, and I blow up 7 points. So this is 9. So C2 of S tilde is actually equal to 89. Okay, so now we do this calculation here. So I get 89 plus 4 times 14, 56, minus 2. Yeah. No, what's the problem? No, I took the self-intersection is, 6, 7. Thank you. But here is correct. But thank you a lot. Okay. 143. Okay? So the intersection number, now, okay, so I computed the intersection with delta, so what's the intersection with the canonical? Well, it's 13 lambda minus 2 delta. So this is 13 times 22 minus 2 times 143, 0. So this is a pity, right? Because we could be finished now if it was minus 1. What? What do you mean it cannot be 0? I mean, no, it's really, of course it is 0. This is 13 times 11. There are points here. I will write C dot like in Tefia. Yeah, it's 0. Believe me, I came up with a lot of, I tried to come up with a lot of plausible arguments why this should be minus 1, but I couldn't find any. That's right, yeah, but they don't. So this is the answer. So essentially, so this shows, of course, something. It shows, for instance, so this argument shows that M16 cannot be of general type already. But it doesn't, by the Buxom company theorem, it doesn't prove uniruleness yet. Yeah. So anyway, this is a step in the right direction. Not general type. So one has to work more. So then, anyway, so this is what it is, yeah? This. No, I'm not. I don't want to. Otherwise, No. So this in itself will show via this. No, but you can now. I leave it as homework, so to say, that to show that K cannot be effective, pseudo-effective now with this. Yeah, it's enough, because if it was, yes, because if K is, okay, so I will describe the general principle, and I'll answer in the process Claire's question, and also Sasha's. So the strategy now is the following. The strategy is to exhibit two divisors D1 and D2 on M16. Two uniruled effective divisors, uniruled, swept by rational curves gamma 1 in D1 and gamma 2 in D2, such that K, the canonical times gamma 1 is 0 and gamma 1 times D1 is positive. The canonical times gamma 2 is negative. And then there is plus a little epsilon, which I don't want to discuss now. And out of this, you will get that M16 is uniruled. And how you get it? Well, because you say that M16 cannot be the canonical, cannot be pseudo-effective. Right, and this is, if it was pseudo-effective, then you would write this in the limit as, say, something alpha times D1 plus beta times D2 plus some other stuff which is effective that doesn't contain either D1 and D2, and you would intersect this relation with both gamma 1 and gamma 2, and you get a contradiction. So this is what you have to, this is a sufficient condition to prove uniruledness. Well, of course you have to produce this D1 and D2, and D1 I already produced. D1 is delta 0, the boundary divisor in M16. The boundary divisor. But D2, for D2 you really have to come up with something more creative that is not reliant on the previous work of Brill-Noether. Well, this is clear here, right? So I did compute it actually. It is 143, which is positive, yeah. Yeah, so yeah, gamma 1 times D1 is 143. Okay. So now, all right, so the second part of the, so the question is how to do this, to to come up with this D2. And this will be done via non-abelian Brill-Noether theory. Okay. So you start with a curve of genus G, and you introduce this notation of the non-abelian loci SU2, omega, and K. And these are the rank 2, so these are the semi-stable rank 2 vector bundles on C, having canonical determinant and K sections or more. So, and this is a Lagrangian degeneracy locus. Of expected dimension 3G minus 3 minus K plus 1 choose 2. And there is a very influential paper of Mukai where these loci have been studied, and their use to the classification of Fano threefolds and so on has been documented. And so yeah, this is in any case these are very interesting loci. So how is this dimension comes into picture? You look at the deformation theory of such pairs, C, E, where you keep the determinant, is governed by something I call the Mukai-Petri map. Yeah, in D1. They are contained in D1, yes.
So if you know that you have the K 16
yeah.
0, and the D1 which is of positive degree, that looks at KD by junction, that the KD1 restricted to gamma 1.
But you cannot conclude that it's uniruled. You don't have negativity to conclude that.
No, what I want to say is that you get from this that the canonical bundle of D1 restricted to gamma 1 is positive.
Yes.
I don't see how it is possible because these curves gamma 1 they will cover the divisor of D1.
Yeah. No, but so I mean, if I would have something like, I would write the canonical as say ample plus something effective. Yeah, and I show that this is not possible now, and so I would intersect this with this curve gamma 1. So I would get here 0, right? So then this cannot, yeah. So I would write here, yeah, that's the point. So I have here maybe delta 0, but so I have 0, and here is positive. It's a contradiction. Right? Because this curve, so how could be this effective part could be alpha times delta 0 plus some other divisors d prime which don't contain delta 0. Okay, but now I look at this intersection. I get 0, ample times gamma 1, this is positive. Delta 0 times gamma 1 is also positive because I prove, and this is positive because gamma 1 is not in d prime, not negative. So then I get a contradiction. And the contradiction comes from the fact that so all this argument buys me for the moment is that it's not of general type. But not more. So I cannot write it as ample plus effective. Yeah, so more than this, you cannot conclude. I don't see how. Okay. So let me go to this non-abelian stuff. So Mukai studied this Mukai-Petri map, right? And so essentially, this is governed by this map. Multiplication map from, so if you have such a bundle, you have this multiplication map from sim2 of A0 of E into A0 of sim2 of E. And the dimensions here are, well, this is obviously K plus 1 over 2 if this has K sections. And the dimension of this, so this is the dimension of the tangent space to the moduli space of rank 2 vector bundles with fixed determinant. And this is 3G minus 3, right? It's not the 3G minus 3 from the dimension of MG, but the 3G minus 3 from the dimension of the cotangent space. And okay, so now you have the statement is that if mu E is injective, then this locus is is smooth of the expected dimension at that point. At the point E. And it kind of, well, Mukai explains a lot about the geometry of this loci for small genus. And then there is an important theorem due to Teixidor. And so what she proves is that if C is generic, then mu E is injective for all E. So this does not establish existence, but it shows that if the locus is non-empty, it has to have right dimension. So this is the situation. And now, of course, so I am interested in the first approximation. So the geometry of this loci is poorly understood. It's a much more complicated situation than for line bundles. So I'm interested first in the situation when this expected dimension is actually equal to 0. Yeah? And so such case is when the dimension is equal to 0 appears when G is actually equal to 16 and K is equal to 9, right? Then the expected dimension is 45 minus 10 choose 2, 0. There is also a very interesting case, genus 13, which I discussed in another paper with Jensen and Peng. But the case is genus 16K equals 9, so you expect to have finitely many such things. And then I introduce this universal locus, so maybe I call it SU 16 omega 9. So this is just the same thing but universal. Yeah, so E is in SU whatever. So you have a map to M16. Okay, so I call this map theta. And here is our first theorem with Sandro Vera. That this locus, this map is generically finite of degree 11. Mu is generically finite of degree 11. So in other words, if you have a curve of genus 16, it has precisely 11 vector bundles, stable vector bundles of rank 2 with canonical determinants and night sections. So 11 is a very low number for, if you go for curves of this, of you know, such high genus. But definitely this is how it is. And okay, so how we do this, I had in mind to explain this, but I'm running out of time. So essentially, we compute the class, the cohomology class of this locus. And well, for this you have to look at Mukai's paper. Essentially, he explains how to set up a determinant. And it's a determinant, you have to, this moduli space is singular, so you have to work on the Hecke correspondence, which is some sort of smooth replacement of it. And you do intersection theory on that, and you set up a matrix. It's a 10 by 10 matrix, symmetric matrix. And entries are some tautological intersection numbers, and these intersection numbers are computed by a famous formula of Thaddeus and Zagier. And you get Bernoulli numbers, and there's a cohomology of the moduli space of vector bundles. And at the end of the day, you know, you have a 10 by 10 determinant, and well, a 10 by 10 determinant you can compute. It's not an n by n determinant, and the answer to your question is 11. And so I do not have a more conceptual understanding of this 11. I would be nevertheless extremely interesting to know this. And I would like to know actually all the number, the cardinality of this fiber for all the G and K where this number is 0. So yeah, in any case, so I would like to now go to the so we have this 11 to 1 cover of M16. It's highly complicated in some sense, and we would like to use it. And I should also say that in the previous case, when genus is actually 13 and K is equal to 8, yeah, then again the expected dimension is 0 in that case. This number, so the degree of this locus, the degree of the Brill-Noether locus, in this case was 11, and in this case the degree of the Brill-Noether locus is actually 3, which is a shocking number. It's a shockingly low because it shows that M13 has a 3-to-1 modular cover. Yeah, so those are cases that are due to Mukai, and the answer is 1 and genus 6. And this, right, that there is vector bundle, yeah, there's a unique bundle. So these are the first cases that are beyond that analysis. And I should say that I have done also genus, the next case is genus 23. And I forgot so it's 5-digit number. 5-digit number, I forgot it. Yeah. The first 2 entries are very low. Okay, so now I have this cover, and what is D2? So I would like to spend some time explaining D2. So the idea is the following. The idea is to, I have essentially only one strategy, and this strategy is to construct a canonical surface on which the curve lies. And which canonical surfaces do you know? Well, complete intersections were good, but they are not enough. Maybe you have also some complete intersections with respect to Grassmannians. And this is the principle that I'd like to implement. So what is the second divisor, this D2? Which one? Sure, but I don't know anything about it. I have no idea how to calculate its class, how to describe it. No, I don't know how, I don't know that, how to, in principle, sure. Actually, this is what I did for genus 13. We did with genus 13. It's a long story. But yeah. So what we do instead the following thing. So the second divisor, D2. Okay, so I will tell you what this is. Is the following. So I will give a definition. D2 will be the locus of dose C in M16 with the property that there exists F, a stable rank 2 bundle with determinant is omega C minus 3 points. X, Y, and Z are points on C. And A0 of F is at least 7. And in light of that result, this is not so strange to consider this divisor. So, and I claim that this is in fact a divisor on M16. So,
in your strategy, you don't really use D2, you only use gamma.
But gamma 2 has to fill D2 up. That's absolutely essential. And also, so in the strategy, my strategy is asymmetrical a little bit. And I just have to point out that the class of D2 I don't know. I'm not able to compute. So this is going to be D2. Okay, so this is a divisor. And so why is a divisor? The point is the following. So you look in this locus, this cover that we constructed over M16. You take a fiber product over M16-3. So a general point here is whatever, quadruple, quintuple, C, 3 points, and an E, where E has at least 9 sections and has canonical determinant. So you look at this cover, and now I look at the following degeneracy locus. I take H0 of E, and I evaluate the 3 sections at the points X, Y, and Z. So this has 9 sections, and this has dimension 6. And the points, so this is an evaluation. And I look at the locus where, the locus where, so those C, whatever, X, Y, Z, E, where this map is not surjective. So it has rank 5, which means that it has rank 5, yes. And out of this, you can show that you can create an F. So if this happens, then there is such an F, which is essentially an elementary transformation of E, and vice versa. So any such F obtained as, who has determinant omega minus 3 points, is an elementary transformation of such a bundle with one of these 11 bundles, and so on, and conversely. So what are the dimensions here? So I impose a condition that this map has rank 5, and I have dimension 5, fiber dimension 3. So this is a codimension 4 condition expected. So you expect to get a divisor on M16. It's a divisor on M16 because it's codimension 4 on this fiber product and the 3-dimensional fiber. So this is of course difficult to prove all these statements. Yeah? But I did a parameter count which justifies this. So now you look at this condition maybe, so why is this the good, right? So I have to, because of the following thing. So it's good because assume now you take a point C in D2. So let's see what happens. So now I can take my curve, and while having such a vector bundle, this gives me an embedding in the Grassmannian G27. Yeah, so this is G27. And here you take the Plücker embedding, which is P20. And of course I have the determinant map to the projectivization of omega minus the 3 points. And I have this map. So this is P12. Okay. So you have this diagram here. So let's call this Grassmannian G. Right? So this is a 20-dimensional Grassmannian. 2 times, yeah. That's what I mean. 10-dimensional Grassmannian. And yes, so then C lies on the intersection of the P12 with this Grassmannian. So, and now here's the point. The point is that you have the 10-dimensional Grassmannian in P20, and you intersect it with a codimension 8 section. You expect to get a surface. And so this is a surface, expected to be a surface. And by the junction formula, the canonical of the Grassmannian is -7, and you intersect it with O of 8, it's a canonical surface. So you have to prove, of course, all this. That for a general point of this divisor, the surface is indeed smooth. But at the end of the day, you have parameterized, so there is a divisor in the moduli space such that the general point of that divisor lies on the canonical surface. And actually a very nice one. So now I will do the same game with the intersection numbers. No, it is a neutral Lefschetz condition. It's a 2-2-2, but the condition that it contains this curve of genus 15 is a non-trivial condition. That's what Claire asked. Yeah. Okay, so I have this surface. Again, it's not the general complete intersection, of course. Yeah, so omega of S is O of 1. And I apply the same sequence as before. OS of C. So I have OC of C, yeah? And by adjunction, this will be just the 3 points. So this, of course, will not move because the curve is not trigonal, but it will show that the dimension of O of 1, so it does move on the surface, is 1. So this produces a gamma 2, a pencil, in M16, pencil. Right, so it's just you vary on this complete intersection, you vary your curve. So now I will do the intersection calculations. yeah, that's what I'm going to do. So I take again gamma 2 times lambda. And this is, well, the same formulas. Chi of OS plus G minus 1. So, and G is 16, so this is 15. And this is H0 minus H1 plus H2. So this is 1, this is 0, and H2, so it's canonical surface. So this is in P12, so this is 13. So the answer is 14 plus 15, 29. And then for the other one, I do the intersection with delta. So this is now C2. And again, I have to blow up the surface at the base points. So there are 3 base points. Plus 4 times G minus 1. And this time I don't have to subtract anything because its general fiber is smooth. So this is 4 times 15. So this is 70, I think, yeah? Okay, and so what is, let's calculate this. So I have the 12 times this. So yeah, I agree. I don't inspire much confidence at this moment, yeah. So in any case, so let me do it, okay. So I computed this. So this is 12 times 14, because chi is 14. Okay, so this is, all right, so do you know what is the degree of the Grassmannian G27? Very good, 42. But I subtract 3 points, so it's 39. Yes. And then this C2 is then 12 times 14 minus 39. So this is 168 minus 39, so it's 129. All right, so now I can compute the intersection number. Gamma 2 times K is M16 is 13 times lambda minus 2 times delta, 13 times 29 minus 2 times 129 equals negative 1. And this is the answer. So, yeah, sorry, I think I did something wrong. It's 189. It's, excuse me, I think I did something not correct here. No, sorry, so this is 129 indeed, yeah? This is 129, so this is 189. Minus 2, 189. Yeah. And this is negative 1. It's minus 1. Yeah? So, of course, I did many experiments to, there is various possibilities, right? So you have you want to have the maximal number of moduli, and you also want to have the right intersection number. Yeah? So I summarize them. So you produce a divisor via this non-abelian Brill-Noether theory, and this divisor has the property that it is swept by rational curves that intersect the canonical divisor of M16 bar negative 1, intersection number negative 1. Now, I do not know what is the intersection, I do not know the class of D2, and I also don't really have a strategy how to compute it. This looks difficult to me. But I have the strategy explained over there. So now I said that you have to produce D1, you have to produce D2, and you have to produce this epsilon here, which I didn't say what it is. But now I will say what this epsilon is. So now you have this, you write down essentially from now on you have that the only thing that you get, that the only thing to rule out, still to rule out, is the following situation, that the M16 is of Kodaira dimension 0. Still to rule out the possibility that the canonical divisor is just a multiple of this D2 and nothing else, with alpha positive. This would not, you have to, essentially, you write your M16 and you assume it's pseudo-effective, you write it as a combination of D2, D1, and stuff that is different than D1 and D2. And you see that the only possibility that you cannot rule out is that this is D2, multiple of D2, and in fact this is rigid. And this is rigid, so that this is a Kodaira dimension 0. So you have to show that this is not possible. And gamma 1 I use at the beginning. Gamma 1 I use at the beginning to get rid of delta 0, essentially. As I showed, that's right. This is the first step. It's not commutative somehow, the strategy. And okay, so here, well, to show this, it's enough to produce one curve in M in the moduli, a curve gamma in the moduli space, such that the intersection of gamma is negative, and gamma is not in D2. Is not in D2. This is a statement that I have to, gamma does not enjoy this property that defines D2. There it is. And for this, I use K-free surfaces. Whatever. I use K-free surfaces of genus 14, two less. So this is a K-free of genus 14. And I take a pencil, and on the pencil I pick 4 points. There are 2G minus 2 points, so there's plenty of points, x1, y1, x2, y2. I take a pencil, and I consider this curve of genus 16 where I identify x1 with y1 and x2 with y2. So this is of course this will not sweep, but this is not a question of sweeping now. This is a curve in the delta 0 of M16 bar. You compute immediately the intersection number of this pencil with the K, you get again -1, and you just have to show this transversality result. And then, well, then you show that this is not possible, because if you had such a relation, you would intersect it with this curve, you get something negative, and on the other hand, it's on the other side has to be non-negative by containment relation. So all in all, this shows that M16 is uniruled. Yeah. So this is the. Because no, because you rule out that. So this is the. So I have here. So at the beginning, if I write it like this, I write the K of M16 as, let's say, alpha times D1 plus beta times D2 plus other stuff that doesn't contain either one. Now you first of all intersect this with gamma 1, and you get here 0. So you get that this is positive. So this will produce that alpha is 0, the first. And it will also tell you something about the slopes of these other divisors. Yeah? And then you intersect what is left with gamma 2. And you show that the only thing left is that's what I wrote there. Okay, so, right, so thank you very much for your attention.